Thank you for introducing me, and thank you for inviting me to present at this interesting session. The purpose of this study is to provide the extent to which the potential reductions in carbon dioxide emissions, CO2 emissions, via private or passenger hybrid electric vehicles in use, HEV in use, have been actualized in real traffic. The research focuses on the transportation field, but you may have similar experiences in other fields such as chemistry and energy, where scientific and technological innovations did not yield the anticipated results, such as emission reductions during the implementation stage. The study revealed that the potential reductions in CO2 emissions via HEVs have not been significantly actualized in real traffic. The number of HEVs in use in Japan has increased rapidly since 2009, and 2020 reached to 10 million, and it accounted for about 1/4 of private passenger vehicles. As you know, higher fuel economy of HEVs over conventional standard and small passenger vehicles, SSV, is important to reduce CO2 emissions. However, the continuous rapid growth in the numbers of HEVs in use is raising the need for comprehensive investigation into the actualization of the potential reductions in CO2 emissions in real traffic. The study was conducted from 3 perspectives. One of them is gaps between test fuel economy in the regulated test and on-road fuel economy in real traffic. The higher test fuel economy of HEVs may be offset by actual driving conditions such as traffic congestion. The second is direct rebound effects. Drivers tend to drive more when use more fuel economical vehicles, and it results in increase in fuel consumption. Such human behavior is known as a direct rebound effect. The third is regional characteristics. The gaps and direct rebound effects vary with urban and rural regions. Furthermore, the analysis was conducted for each year over the study period to minimize the influence of the changes in the other socioeconomic situations on the result. The gap is given by this equation, dividing on-road fuel economy by the test fuel economy. The direct rebound effect is quantified by the elasticity of delta CO2 VKT with respect to improvements in the on-road fuel economy of HEVs compared with SSVs, where delta CO2 VKT is the contribution of the vehicle kilometers traveled, VKT per vehicle, to the aggregate differences between CO2 emissions per HEV and SSV. And the delta CO2 VKT is estimated by the modified Raspberry index composition MLI decomposition proposed in my other papers. When CO2 emissions per vehicle are determined by three change factors such as test of fuel economy, gap between on-road and test of fuel economy, and VKT per vehicle, CO2 emissions per vehicle is given by this equation. The MLI method quantifies the relative contributions of the three factors to aggregate differences between CO2 emissions per vehicle and SS3. Then, delta CO2 VKT is used for estimating the direct rebound effect. This slide shows an example of the index decomposition result in the urban region from 2010 to 2013. In this figure, delta CO2 VKT, shown in green, is used for estimating the direct rebound effect as explained. The period covered by this study spans from 2010 to 2020. The number of HEV in use rapidly increased nearly threefold from 2010 to 2013 and continued to grow nearly threefold from 2013 to 2020. The areas selected are Kanto and Tohoku regions because these are representative of urban and rural regions in Japan, respectively. The Kanto region has the highest population density with the lowest vehicle kilometers traveled per passenger vehicle and contains large cities such as Tokyo and Yokohama, where modes of travel other than passenger vehicles are available. By contrast, the Tohoku region was very low population densities with longer VKT per passenger vehicle and contains small and mid-sized cities and villages, where transport needs are mostly met by private passenger vehicles. The statistical data used are available in the public domains. However, the values of yearly average test fuel economies were assumed due to the unavailability of VKT data for each model of all private passenger vehicles. Hence, the values were obtained from representative models of HEVs and SSVs in Japan. The estimation result of on-road fuel economies showed that the on-road fuel economy of HEV in both urban and rural regions were higher than those of SSVs by about 60% on average. Moreover, the on-road fuel economies of HEVs and SSVs in the urban region were lower than those of the rural region by 5 and 8%, respectively, on average. The estimation result of gaps of both HEVs and SSVs tended to improve slightly over the period in both urban and rural regions. However, the higher test fuel economy of HEVs decreased to 52 and 55% in actual driving in urban and rural regions, respectively, on average. Whereas The test fuel economy of SSVs decreased to 66 and 71% in urban and rural regions, respectively, on average. That is, the potential reductions in HEV CO2 emissions have been significantly offset by the deterioration of fuel economy in real traffic, particularly in the urban region over the period. The gaps between the test and on-road fuel economy vary with many factors, such as regional traffic congestion, speed, and accessory use such as air conditioning. And the heavier traffic congestion in the urban region than the rural region may lead to a decline in on-road fuel economy of HEVs. The estimated direct rebound effects in both urban and rural regions were 21% and 23% respectively on average. That is, an 1% improvement in the on-road fuel economy of HEVs would induce an increase in CO2 emissions per HEV of about 0.2%. The direct rebound effects tended to increase from 2010 to 2015. The period was in the early stage of HEV introduction in the market. Better driving experiences offered by HEV, including comfortable start acceleration and less noise, may contribute to an increase in direct rebound effect. Furthermore, since 2016, the direct rebound effects have remained relatively constant, without noticeable differences between the urban and rural regions. As we have seen, the gap and the direct rebound effect of HEV use have significantly reduced the expected reduction in CO2 emissions to a degree that cannot be overlooked. Furthermore, neither has improved noticeably. So, what measures are required for mitigating the deterioration? For this, an integrated approach would be required. This includes implementing a fuel tax, such as congestion charges, improving road infrastructure, utilizing advanced traffic and signal control network that use real-time data, vehicle sharing, and encouraging ecological driving practices. Particularly, raising fuel prices through the increased fuel taxes would be one important measure. Higher fuel prices would induce a reduction in travel distance, consequently reducing the direct rebound effect. This would result in decreased traffic congestion, especially in urban regions. Hence, on-road fuel economy could improve, and the fuel economy gap would reduce. However, such a market-based measure would have different impacts on travel costs in rural regions where locals rely on private passenger vehicles for transport. Hence, the implementations of regional equity policies is essential, such as using revenue from increased fuel taxes to make public transportation more convenient in rural regions. The potential reductions in CO2 emissions via HEVs have been significantly hindered by the fuel economy gaps and direct rebound effect in real traffic. Thank you.